and submerged bodies. In some problems, we maybe have, let me write a introduction. Many fluid problems do not involve motion, they concern the pressure distribution in a static fluid, pressure distribution in a static fluid. And its effect on solid surface and on floating. So floating and submerged bodies. So if a problem do not involve the fluid motion, let me write it, no fluid motion, pressure distribution in a static fluid is concerned, and the problems can classified in the pressure distribution in fluid. When the fluid velocity is zero, depending on as the hydrostatics denote as the hydrostatic condition, the pressure variation is due only the weight of the fluid. Assuming a non-fluid in a given gravity field, the pressure may easily be calculated by integration. Important application in this chapter are, this chapter important for pressure distribution in the atmosphere and the ocean. Writing pressure in and oceans. And second, the design of manometers, mechanical and electronic pressure instrument. Manometer, mechanical and electronic pressure instrument. Meter, electric, mechanical and electrical pressure instrument. And third, force on submerged flat and curved surface. Force on submerged surfaces buoyancy and submerged bodies. The behavior of floating bodies. Are the application of the pressure distribution. Are listed as these 5 case problems. Next, we are going to have a definition for pressure and pressure gradient. In the previous chapter, we saw that a fluid at rest cannot support shear stress, and a more circle for analyzes the stress reduced to a point. In other words, the normal stress on any plane through a fluid element at rest is a point property called the fluid pressure P. So we have a definition. The normal stress on the any plane through a fluid element at rest is a point property called at rest is a point properties called the fluid pressure P. It is definition P taken positive for compression by common conventions. This is such an important concept that we shall review it with another approaches. Consider this figure as a small body of fluid at rest. As this picture, at rest of size of delta x by delta z by delta s and depth b into the, in this case, into the blackboard. So we have the dimension here and delta s, z direction, x direction, and 3 pressure, hydrostatic pressure on an element of fluid, pressure also in this direction, and also element weight of the element as this picture. We can write the equation of equilibrium. We have 2 direction of forces. F x equals to 0, fz equals to 0. In the x direction we had the pressure P, and the pressure multiplied to the area equals to the force. So in x direction we have x, b, which is a, and p, plus equals to minus pn, this force, multiplied to the area in x direction, sinus theta equals to 0, and also we have in y direction, in this case z direction, p, z, p, let me have a correction here, delta z, delta x minus p and b delta s in y direction, minus the weight effect rho g b delta x delta z, that is v m rho v equals to m. So with the, if we simplify this relation, we can calculate, obtain this relation for, we had this relation delta s sinus theta equals to delta z and delta s cosinus theta equals to delta x. So with replacement we can obtain this relation px equals to pn, and also pz equals to pn plus the weight effect on the fluid element. In the case the limit as the fluid bed shrink to a point, so delta z tends to 0, so we can write px equals to pz equals to pn equals to p. Since theta is arbitrary, we conclude that the pressure P in a static fluid is a point property independent of orientation. So it is the derive relations to admit that the pressure is a point properties in the fluid. In the next, we have a pressure force on a fluid element. Description: pressure force on a fluid element. Pressure causes a net force on a fluid element when it varies spatially. So let me write. Pressure causes a net force on a fluid element when it varies spatially. To see this relation, consider this picture for more description. The pressure acting on the two x faces in this figure can be written as this expression. So let me bring a picture here first. Consider the pressure acting on the two faces of an element of fluid as is shown in this picture with these arrows. Let the pressure vary arbitrarily, like we had P equals to P x, y, z, and t. The net force on the x direction on the element in the figure in the x direction is, we can write dfx. Net force in x direction, P multiplied to the area, and minus again P, which is x expression multiplied to area. This is the net force on the element. In like manner, the net force dfx involves the gradient of pressure in the y direction, and net force in the z concern the, again, for example, it is in the x direction. We had for dfy equals to, for example, we have p dx dz minus p plus ln p on ln phi dx dz, and in z direction we have dfz equals to p dx dy minus p plus d by dx. In three direction we can write these equations for the net forces. With simplification we can obtain the, for example, in this relation, and also eliminate with simplification of this multiply parameters. So we can write dfx equals to minus ln p ln x dy dx, dfy minus ln p ln y dx dz. And dfz equals to dx dy. This expression can be written as in a vector form as this. Let me expression. So we can write net force on a fluid. df in the previous section we should write here delta x and delta x. In this case, delta x, delta y, delta z, and we can write the expression as minus excuse me. Delta Z. We recognize the term in parentheses as the negative vector gradient of P, denoting F as the net force per unit element volume. We can write the expression as below. So equals to gradient of P in the vector form, where gradient operator is so. As you see, it is not the pressure, it is a pressure gradient causing a net force that must be balanced by gravity or acceleration or some other effects in the fluid. Equilibrium of fluid elements is our next description. The equilibrium of fluid element will be discussed in next video. To have a better definition and also